is going to be a little different from the last one. It is going to be much more conceptual, a little bit of neurosymbolic architecture 101. But I have been talking to people, and you've been telling me that you haven't necessarily come across this term. So that's my goal, is to introduce this to you tonight, and also to maybe hopefully inspire you. I know this is AI Tinkerers, so I would like to inspire you to do some tinkering on this front. I will say that effectively, even if you don't know it, you're all already doing tinkering on this front. So I'd like to sort of encourage you to increase your activity, maybe apply it to that contest that was just mentioned and see how that can go. Okay, so who am I and why am I talking to you about this? Well, I am an adjunct professor at Carleton. I am in the cognitive science department there, which is one of sort of the AI departments in some ways. And then in addition to that, that's not my day job. I'm sort of a volunteer professor in some sense. And then my day job is as a practicing data scientist. I've been a working data scientist. I have a company that's a data science consulting company for about a decade now. So today, like I say, it's going to be a bit of a 101. We're going to talk about what are neurosymbolic architectures and how can you start using them, if you decide you want to, after I've explained to you what they are. Before I do that, though, I'm going to give you some context, because I think the context is really important. And if I don't give you that context, you might not know why I think it's a good idea for you to try them out. And in giving that context, I'm going to give you sort of two perspectives here. I'm going to give you the researcher perspective, and I know that there are some researchers here tonight. And then I'm also going to give you the sort of industrial social perspective. And I'm going to do this starting back from when I got into grad school, which was basically in 2000. So in 2000, you'll see that there's a theme here, what the researchers are up to. Hint, they are researching. So we have the researchers in 2000, and what is happening with them is they're researching good old-fashioned AI. We'll get to what exactly that is in just a minute. So they're researching good old-fashioned AI. There is machine learning, okay? So, I was doing these little side projects in neural nets, but that was considered to be very fringe, like why are you doing that? Then meanwhile, in industry and society, I would say what I was up to, and people would kind of look at me and they would go, oh, so you're building data from Star Trek. And we'd be like, no. And so fast forward a decade, what are the researchers doing? They're researching. But now deep learning has appeared on the scene. And I will say that if you go to the Wikipedia article, it tries to sort of suggest that deep learning has been around for a really long time. It's a bit mysterious. But in my experience, I want to say that deep learning really appeared in the, I would say that 2007, Benjo and LeCun's paper, Scaling Learning Algorithms Towards AI, where they talk about, these deep architectures, was really when this kicked off, in my opinion. What's happening in industry and society? Well, there is starting to be a bit more of a penetration into this space, but there's so much hype. There's so much hype that there's just a huge amount of skepticism. Because a lot of the time people are trying to say that automation is AI, the use cases are difficult to come by, but it's starting to get in there. What a change a decade has made, I want to say a year has made. What are the researchers doing? Well, guess what? The researchers are still researching. And what are they researching? Well, they're starting to research sort of what is going on with this deep learning stuff, but they're also trying to add some new pieces to it, and that's kind of a little bit of what I'm going to get into today. I will say that things have kind of leapfrogged in terms of the industry and society front. In the social front, people are suddenly like, AI is a real thing. And also people often think that ChatGPT is just AI or vice versa. And also, surprisingly often, that it's somehow artificial general intelligence, which, as we'll see, is probably part of the hype train. What is really interesting, I think, is how much progress has been made just by throwing things at the wall and seeing what sticks. I really do think that the current AI explosion has been a result of a lot of activity on the engineering front, right? So the engineers have just been sort of saying, let's see if I can make this work this way. Let's see if I can make this work that way. That's not to say that they haven't been inspired by various research domains and various even other domains like biology, really thinking about how that might work. But there's been a lot of throwing things at the wall. And like I say, obviously this has been working so far. But I would say also that some theory has been lagging behind, and we would really like to see that theory piece come in. And I think if we do that, and hopefully this talk will also convince you of that, it could have a very interesting and galvanizing effect on our approach and what we're doing. So with that in mind, what can we expect to see next? Or maybe I should say, what can we expect to see right now? So Hai convinced me to give this talk a few months ago. And I was like, yeah, I don't know, this neurosymbolic thing could be heating up, could be getting interesting. And then in January, last month, some of you may be aware that Google released a model called alpha geometry. Who has heard about this coming out? Some of you, okay. So the big news here is that alpha geometry can solve complex geometry problems. Emphasis there on the geometry piece. These are not just any old math problems. They're geometry problems, which have traditionally been very intractable on the AI front. And as the MIT review article says, why is that? Well, compared with text-based AI models, there is significantly less training data for mathematics because, and this is a key word, it is symbol-driven and domain-specific. So how did they tackle this? Well, I encourage you to check out the open access article. It's nice that it's open access, solving Olympiad geometry without human demonstrations, and you can get the code from GitHub. But if you look at that article and you look at what they're talking about, in figure 1, you can see overview of our neurosymbolic alpha geometry and how it solves geometry problems. So increasingly, I think you're going to be seeing this word, and it could be good to have a sense of what it implies. So with that, let me give you a little bit of vocabulary first. So what is good old-fashioned AI? Like when you think of what is good old-fashioned AI, what do you think of? Maybe some of you have never really encountered it, and you don't really think of it much. But if I was to describe good old-fashioned AI to you, I would say, first of all, it is very focused on symbolic representations of knowledge. Also, really importantly, and this was part of the reason why it was overtaken, the models in this space are essentially at least partially, if not completely, built by hand. There is no automated learning in this space. If you want your model to do something, you have to construct it to do that. And like I say, the focus here is really on symbol manipulation. There really is no semantics easily won in this space. So it's a very symbol syntax-focused endeavor. Classic machine learning is kind of this bridge. I'm calling it classic machine learning now, even though it used to just be called machine learning. But classic machine learning is a bridge. So what do we see? We see this grab bag of techniques that are kind of not too related to each other, but maybe in some sense. Decision trees, support vector machines, statistical approaches. But one of the things that tends to unite them is that we no longer have to construct the models themselves by hand. We're running algorithms over data to construct the models that we're going to use. And this is really what gets us to the deep learning piece, right? So neural net architectures, the models are built by running the algorithms over the data, but also our representation of knowledge, of information, importantly has changed. And so we start to see this representation that people talk about as being sub-symbolic, or, and I'm going to say this is kind of a bit of a gloss, it's numeric. And also what we're starting to see is people sort of arguing we're getting something semantic, something related to meaning and not just syntax out of what we're doing. So this is sort of this evolution. But you might be wondering, like, why were people so dedicated to the good old-fashioned AI approach? Well, it turns out that it wasn't just because it was the only approach available. We did have access to the concept of neural nets. It was largely, I'm going to argue, driven by something called the physical symbol system hypothesis. And this is a hypothesis that has not yet been disproven. So this basically says that symbols and symbol manipulation are both necessary and sufficient for intelligence. And what that means is if you don't have symbols, then you can't get real intelligence. And if you do have symbols, you have enough for intelligence. And this could still be the case. And if it is still the case, that means that deep learning architectures, if you believe that they're subsymbolic, are inherently limited in some sense. Controversial may not be the case. There are other options as well. For example, Rodney Brooks would say that's not the case. In fact, the necessary ingredient for intelligence is action and embodiment in the world. So not the only options, but definitely it's a very prevailing hypothesis. And it's one of the reasons why people have been so fixated for a long time on these good old-fashioned AI models. So no surprise, it's there right in the name. What if we could just have the best of all worlds? Why wouldn't we want to combine all of the work that had been done on the good old-fashioned AI front with everything exciting that's coming out of the machine learning space? So clearly, Google thinks this might be a good idea. And so the question is, how do we do it? And how do you do it? Well, it turns out that in terms of how you do it, and this is a new discovery for me as well, there's a bunch of researchers who have been quietly working away on this for a really long time. And so they've put a lot of thought into this. And their definition of neurosymbolic computing is simply that it's something that seeks to bring together robust learning in neural networks with reasoning and explainability via symbolic representations, basically using reasoning engines. And so it has a long history, but it's been niche until now. And so one of the things I like to do is run around these days and tell people about it and say, check it out. But we can see it got started even in 1994. People were, even in 1994, talking about a perspective on the state of the art of neurosymbolic architectures. And then Algebraic Mind in 2001, right up until 2022, yet another state-of-the-art paper. So people have been working on this, and it's probably a ripe area for kind of more societal, industrial discovery. And sure enough, we are starting to see industry moving into this space. I showed you the Google example that came out in January, but before that, I was just going to show you this example because I didn't know about that before. This was an example from 2022, AI21 Labs. They are the lab responsible for creating the Jurassic 1 language model. And even then, they were saying, you know what, we need to add in decision engines, knowledge engines. So they developed their Miracle system, which is a modular neurosymbolic architecture that combines large language models and discrete reasoning with knowledge sources. And so this is basically their effort at the time. This was before, as far as I know, before GPT-4 came out. And they wanted to find ways to deal with the weaknesses that people were seeing in large language models. The key question to think about if you want to implement some of these architectures is the encoding. This is kind of your way into thinking about it. And you can think about it in terms of the input encoding, and you can think about it in terms of the inner encodings and processes that are happening, and then you can think about it in terms of the output encoding. And in each of these cases, you basically have kind of these two options. The neural option, which as I've mentioned is sort of this numeric continuous representation, or the symbolic, and then you get to mix and match. If you're interested in this, I would recommend checking out Henry Kautz's taxonomy of neurosymbolic architectures, where he basically kind of goes through all the mixes and matches and gives you examples of what each one might look like. However, I'm going to give you one specific example here. And like I say, I think this is my goal. I want to inspire you to try this approach out and to experiment with it yourself. And I think it's a very rich area for investigating and tinkering. So what I'm going to do now is going to give you kind of a worked example that I created for this presentation and for this evening that gives you kind of a very little taste of what this might look like. I don't get to do much implementation these days, so this was a nice opportunity for me. So what does this toy example look like? So I have this on my laptop, but I didn't really want to test the demo gods this evening. So I'm just going to show you kind of the outline of it, and then if you want to see it, you can come and see me on my laptop after. So the way I constructed this demo is, so I decided, well, I'll just use GPT 3.5 for my neuro component. I did a little hacking to do a little data transformation because unfortunately GPT 3.5 couldn't quite cut it on that front. And then for my reasoning engine, I used a production rule system. Curious, has anybody encountered production rule systems before? This is very, very old-timey, good old-fashioned AI. I see nobody has seen this. Okay, so that's great. And just if you want to try this out, I will mention that what I did to implement this, I used something called GACTAR, which was created by a friend and colleague of mine, Andy Maloney. So what he did is he took some academic models in this space that are sort of meant to model human cognition, and he put a nice wrapper around them so that you can use them in a less academic context. So if you want to try out a production rule system, you can access GACTAR. It's on GitHub. And then because I'm a classic data scientist, I could not leave out the classic data science piece, and so followed this all up with a little bit of a graph output using R. Okay, so symbolic input. So this is my symbolic input into ChatGPT. Please give me 20 facts about cake in the form subject, verb, object. Now, it is the case that behind the scenes, of course, GPT then converts it into this neuro subsymbolic input into the large language model. So that's where, so we have symbolic going to neurosymbolic, subsymbolic. And then we have the conversion back to a symbolic output from ChatGPT. And you'll notice it didn't exactly do quite what I wanted it to do. It did try. People bake cakes. Cake ingredients include flour. Then it felt the need to give me some more interesting information, but that's OK. Then I was like, that's what I had to do my little sort of hacking. And by the way, so at this point, what I've done to this point would be considered a symbolic neural symbolic architecture. Not that exciting. This is why I say you've all kind of been doing this already, but that's a very vanilla way of thinking about this. Where we go next is we want to say, OK, we've gone symbolic, neurosymbolic, but I want to extend that symbolic piece by feeding it into a reasoning engine. So my tweaking of the syntax turns the facts into this, and I take that symbolic input and I put it into my production system. And my production system looks like this. So this is an overarching architecture for all production systems. There are variants. But basically, the way it works is you have your memory, which is a knowledge base, and then you have buffers. And the buffers work to allow you to match conditions that you specify. And if those conditions are matched, it leads to a production, which is essentially a function firing. Usually when those functions fire, they do things like move knowledge from memory into a buffer, and you end up with a cycle. And this allows you to do chaining of facts or knowledge leading to a certain type of reasoning. In my case, I made a little fact chaining production system model in GACTAR, and I chained a bunch of facts about cake together. Cake is baked by bakers. Then it says, OK, I'm going to find facts about bakers. I'm going to find more facts about bakers, and then I'm going to connect that to cake batter, and then I end up with this connection between cake and cake batter, which was my goal. And so that, in a sense, is giving me information in a symbolic processing fashion about the relationship between cake and cake batter. And then, if I want to, I can turn this into essentially a concept web. And so it's a way of taking raw facts, which are pulled out of a large language model, transform them a little bit, used a good old-fashioned AI system, a production system, to do some reasoning over them, and resulted in something potentially useful from a knowledge perspective. So this is kind of a trivial toy example, but I wanted to show it to you because it's using tools that you have access to, and I hope it gives you a little taste of essentially what they were kind of doing in a much larger way when they made that Google alpha geometry architecture. So I think I'm over my time. So I just want to conclude by saying I really think that this potential partnership of neuro and symbolic can be quite exciting and interesting. I hope it will breathe new life into a lot of old techniques. And I think it can increase the power of new techniques at the same time. So thank you very much. If anybody has questions, I think people are being directed potentially back there, or maybe I can just take them from the audience. If you have a good projecting voice, yes.
Yeah, you mentioned you have toy examples. Are there any non-toy examples that actually publish their findings that we could look at? So for example, that diagram you made, is there a actual real world or industrial diagram of that knowledge and how to actually use it?
So when you say, I guess I'll give you two answers. So I will say this is a new area for me too. So I'm like all of you, I know about the two pieces, but not so much them together. I mean, I actually think that the best example I would know about would be the alpha geometry example that I put up there. They actually have a really nice, that paper is really nice. I would suggest checking it out. I don't know if you're wondering about sort of the concept map idea, that I would direct you to semantic web ontologies, and I know you know about that. So, yes. Any other questions? Oh, I think there's maybe one up here.
Hello. Well, I have a question on training. So we love AI because we can train it.
Yes.
And we can train it because we have everything, every operation is differentiable, and we have cool optimization methods for differentiable functions, and also we can implement it all in parallel on GPUs and stuff. So the question is about symbolic parts of your systems. So how do you train them? So isn't it just an AI plus some rules from the real world that the researcher knows?
Yeah, okay, so there's a couple of questions bundled up together there. There's how would you train some of these classic methods? But then there's also this question of, well, isn't it just programming, right? So those are actually two separate questions. In terms of the training question, I think that's an excellent question to be asking, because if we think about neural nets themselves, one of the huge blockers for them to being used, people knew about the neural net architecture, but there was no backprop algorithm that people knew about for a long time. And so people would try to actually build, I mean, this is way back in the day, but people would try to build these neural nets with the weights set by hand. They didn't get anywhere until somebody came along with the backprop algorithm. And so I think it's an interesting question now to ask, could we come up with the equivalent of the backprop algorithm for some of these good old-fashioned AI architectures? That's a great open question. In terms of the isn't this just programming, I guess I would say, in a sense, it's all just programming. But so one of the things that does make it interesting is if you have certain architectures, and for example, you can find ways to train those specific architectures, then that takes it out of the sort of just programming space. Yeah, great. I think you're asking exactly the right question. So. Anybody else? No? All right. Well, I hope I have inspired people to give this a shot, and thanks very much.